Hello. Thank you to Dockyard for organizing this. I'm Sheena McCoy, and I work at ModCloth.
And I'm Rachel Myers. I'm a developer at GitHub. And this is who we are on Twitter. All of our references that we're going to talk about in our talk are linked to in this bit.ly bundle. And after the presentation, we're going to upload our slides there as well. So one-stop shop for everything. We also themed our presentation. Depending on which one of us you ask, it's either based on Jurassic Park. It gets better. Or The Land Before Time. Hopefully it's entertaining either way.
We're going to dive into the internals of the Ruby virtual machine, specifically how Ruby handles method lookups. Since Ruby is delightfully dynamic, we might expect this process to be slow. And that's true. We're going to walk through why this process was slow for Ruby 1.8 and before. A huge improvement came in Ruby 1.9 when Yard became Ruby's reference implementation. Finally, we'll walk through the limitations and improvements since Ruby 1.9. But first, let's talk about what will and won't be in this talk. There will be velociraptors.
So this will not, however, be a performance talk, at least not for most people. This morning, Matt Aminetti said that if you're writing Ruby, you probably don't care about performance. That has not been true for me. But it's true that when people work on method caching, they're doing it because they want to improve Ruby's performance. This is especially, this does not mean that Ruby is the cause of your performance problems. This is especially true if you're using Ruby to write websites. In that case, you will almost certainly have dramatically bigger performance fish to fry. Yay, emoji, I didn't have to draw that. So things like optimizing for a faster web page by, wait, go back. More fish. You get more fish. Okay. So some things that you can do to optimize your website are mostly on the front end. Things like gzipping your assets, minifying and concatenating and ordering your JavaScript well, generally reducing the number of total requests that you're making for a page, spriting your images, combining style sheets into one cacheable asset can cut way down on your time to window load. So you can optimize for seconds or you can optimize for milliseconds. That is the message here. So I care a lot about this stuff. I gave a talk a couple months ago about how our app became hard to measure when it became mostly JavaScript. We're not going to talk about, we're not going to talk about any of that stuff today. So if you think that I'm going to tell you how to make your website faster, you're wrong. You should go no. On to what we will talk about.
So that being said, some programs, especially those running on embedded hardware or those supporting extremely high-load websites, really do care about maximum performance. If you care about this level of optimizations, we have some thoughts there too. But maybe a better reason to understand Ruby's method cache is because it's cool to learn and know about the stack. Someone could say that we're the wrong people to give this talk. Neither of us commit to MRI. But that was also the appeal to us. Jumping into the Ruby internals are out of norm for both of us, so it was a lot of fun. And that's the best reason to dive into this stuff. Learning a part of the Ruby interpreter is an awesome way to nerd out. Sure, we got sea dust all over our cool Ruby clothes, but we had fun. And we want this stuff to not feel out of reach for people. So when we use jargon, we're going to try to say what we mean. And our references include a few files if you want to jump in.
So that's what we're going to cover. Let's do a quick primer on how some other languages avoid the problem of slow method resolution. To start off, I drew that one. To start off, let's talk about what method caching is in general. Method caching is a way of speeding up method lookups by storing the result of the lookup the first time you encounter it. The next time you hit that same call site, you can hopefully look it up quickly in the cache rather than resolving the method call again. For example, this instance of Raptor invokes rar. That's so fun to say. And we don't know quite where we should go look for that method definition. Is it in Raptor? Is it in Dinosaur? Is it in an included module or in a superclass of Dinosaur? And there are, of course, more possibilities. In Ruby, it could be defined in many places, or it could be defined dynamically. So figuring out that method resolution could be computationally complex.
So just for context, the problem of expensive method lookups is sometimes made a lot easier in other languages. For example, compiled languages add optimizations during compilation to significantly improve the speed of method resolutions. For example, in C++, if the method rar is not overridden, the compiler can just substitute the method name for the direct method address before the program is ever executed, negating the need for a method lookup. They can call the address directly. If the function is virtual, however, then rar can be overridden, and an extra step is required to determine what class the function rar is defined in. Instead of a direct jump, the method address is looked up in a vtable. In this instance, there's one virtual table for the raptor class, regardless of where rar is defined, in dinosaur or in raptor. The virtual table for the calling class returns the address pointer, and then the call can be executed. And a third option for these languages is specifying the function as inline. In this case, the contents of the function is copied directly during compilation. Not only is no lookup involved, but there's no jump either.
But it can be harder for interpreted languages to have a quick method lookup. The method address of a particular method can change at runtime. Python, however, has a cool solution. So Python includes late binding. That means the interpreter doesn't know what type raptor is until runtime. And unlike being able to compile the address location in the machine code like in C, the interpreter still needs to search when rar is executed. So to make the search faster, a dictionary is set on the class with the address of all the methods. In this example, if rar exists on raptor, then the interpreter can merely search on the class's dictionary and jump to the address location that's returned.
So that's how method resolution works in a few other languages. Now let's take a look at how it works in Ruby. But before that, it's time to define some jargon. We're going to discuss MRI through this entire talk. We're using it interchangeably with Ruby, although there are several other Ruby's interpreters. We're also going to discuss the virtual machine through this whole talk, because the Ruby virtual machine is what's responsible for resolving method lookups in our application code.
So let's jump into how MRI looks up a method up through version 1.8. We're not just doing this as a history lesson. It also is going to demonstrate for us the problem that method caching is solving. So here we have a basic example of a method invocation. We have an instance of raptor, which can get some behavior from dinosaur, and now we're going to send it a message to rar. Let's see. There we go. Unfortunately, at this stage, it doesn't know immediately where the method is defined, and the VM doesn't. We don't know where the method is defined, and the VM doesn't either. So first, we're going to look inside the raptor class. If we don't find the method definition there, we're going to go look into the included module. So we don't find it there either. Still not finding it, we're going to go up the raptor's hierarchy and check in dinosaur. And there we find the method definition. This is where, as Ruby developers, we're going to pay the price for not having to define the interface or dictionary. Instead, we have to check up the hierarchy every time. So you might feel that that's just the way it has to be, that there's nothing to be done. We have to resolve our methods, and this is how that happens. But let's look at what happens when we invoke the same method 10 times. In Ruby 1.8, we're going to pay the cost of that full method resolution every single time.
Now we're going to jump on to see what's going on under the hood. We're going to talk about the steps that the Ruby 1.8 interpreter uses to look up a method. Tokenization is the first step in creating the abstract syntax tree. When I first started researching method caching, I found myself needing to step further and further into the internals of Ruby to answer all of my questions. Ruby Under a Microscope by Pat Shaughnessy was a great reference for me, so I added it to our Bitly bundle. So let's dive into this one line of Ruby code to see how it's executed. The first thing that happens when we run our dinosaur Ruby script is that the MRI groups the characters into tokens. Because Ripper, the Ruby tokenizer, ships with Ruby 1.9 and 2, I was able to see how all of our examples were parsed. It's an obvious but important step to executing this line of code. Ripper does lexical analysis, scanning character by character to group the string into a recognizable entity. In this example, Raptor is the first string that can be classified. It is stored as an identifier in an array of tokens. The period is identified and stored next in the array. And finally, the last identifier, rar, completes the scan. Now that Ruby has this array of tokens, the next step is to group them into expressions that Ruby can understand and execute. Just like there are grammar rules in the English language, there are grammar rules that the Ruby parser Bison uses to make valid statements in Ruby. Ruby's MRI parser is grouping expressions in order to create the abstract syntax tree. The Ruby 1.8 interpreter uses the output of this expression tree to directly walk, search, and execute the code. Bison classifies Raptor as a variable dereference call, and then classifies raptor.rar as a call on an instance by saving it as a node on the tree. And finally, all of this is stored in a program node. Normally, the program node would contain a variety of different method calls necessary to execute our script. But in the spirit of simplicity, we only have raptor.rar in this example. And this is the abstract syntax tree for raptor.rar. As you can imagine, it would grow in size and complexity for a real program. As I mentioned before, Ruby 1.8, the interpreter walks this tree to execute the code, and when it finds rar, it also has to search the tree to find where it's defined. It doesn't do this for just the first time that rar is called. It has to search the tree for every method resolution.
So in 2007, Yarv, another Ruby interpreter with a performance focus, was merged into MRI. One of the optimizations that Yarv made was to prevent having to complete that full method resolution for every invocation. Instead, it would resolve the method the first time it was encountered and save the result of that resolution. So in our example, calling raptor.rar 10 times, this means that we only have to resolve the method once, and the next 9 calls can be faster. In this particular case, we tried to benchmark this, and the time saved was, as you would expect, pretty trivial, but it can become noticeable in large, complex applications. For reasons we'll touch on later, how much time a program saves by caching a method lookup is really dependent on the code itself. There are things that our code can do that will prevent us from getting the benefits of the method cache. So first, before we get to that, let's walk through our new optimized version of a method resolution. We're going to refer to Yarv and Ruby 1.9 interchangeably, and we promise to only show bytecode on a few slides. So this is our code that we're going to run a few times in Ruby 1.9. The first thing that's going to happen here is that our code will be tokenized into a stream of tokens and parsed by Bison into an abstract syntax tree. Just for kicks, here's what the AST looks like for this one particular block. So we can see the tokens of our original Ruby in red. The result of the tokenizing is in light blue, and everything added by Bison is in dark blue. At least that was my goal. I was syntax tiling this by hand, so. And that abstract syntax tree will be compiled into bytecode. Here's one section of that. As the program runs, we update it by filling in the placeholders that are left for a cache entry in each lookup. When a method is resolved, it appends the location of the cache and the generation that the program was cached in. This is called the inline method cache, and this will optimize lookups for both constants and method calls. So the Raptor constant is cached similarly to method caching. To method calls. Also, raptor.rar is going to call opt_send_simple, which is similar to the send method. Opt_send_simple is going to save the method address to the cache, as well as modifying the bytecode to include that inline cache object. So now that we have inline method caching in Ruby 1.9, we can see how this shortcut is going to play out. With inline method cache, a placeholder is left in the compiled code for method addresses. And when it executes rar, if the placeholder is empty, it's going to save the address of the method after it searches raptor, dinosaur, and all the other possible locations. If the line is executed a second time in the program, it doesn't have to search again. So again, we're noting the state of the program or the generation when the method lookup was cached. We're going to need this later when we need to check if the cache entry is still valid. So this is a good point to introduce our global counter. This is the way that Ruby is going to keep track of the generation. The exact variable in C is the Ruby VM global state version, but we're always going to refer to it as the cache generation or the global state of the program. And just as a side note, because this is kind of cool, I wanted to take a slide to talk about the caching style that's being used here. So Ruby is using a pattern called generational caching, and that means that Ruby is going to keep track of its program state, and when a method resolution is cached, the cache entry notes that generation. So some events that we're going to cover soon are going to spawn a new generation, meaning that the event changes the program in such a way that everything that was cached up to that point can no longer be valid. So the really cool thing about this, do you guys get the Jurassic Park reference? Yeah, okay. No one's going to die this time, though. It's okay. The thing that's cool about this style of caching is that it's really low overhead. So we don't have to call a purge all event that's going to sweep through all the bytecode and remove all of our cache entries. That would be slow and potentially unnecessary, because if a method's never going to be called again, why should we worry about its cache entry? So generational caching means that we only have to increment the global counter for certain events. And before we use that cached result, we're going to compare the generation in the cache with our current generation. If there are any Jurassic Park fans in the house, I was tempted to put a gif of the game warden realizing the raptors had been hunting him while he was hunting them, but it's a little bit graphic. So just a quote instead.
So let's recap where we are. The Ruby 1.8 interpreter was resolving methods from scratch every time. It's like a server that has to fetch a response on every request. So Ruby 1.9 avoids that. It's a giant re-implementation of Ruby that's creating bytecode to optimize the need to search the abstract syntax tree. The way that it optimizes the method lookups is that after it finds the location of the method the first time, the interpreter then stores the address of the memory inline in the bytecode. The tricky thing about caching anything is knowing when to invalidate the cache. This is going to be especially true given all the ways that Ruby lets us dynamically change the set of methods available to an object. And here we're defining some slang. Cache hit is when we're able to use the cache entry, and we bust the cache when we invalidate it. It's also possible to not use the cache, so have a cache miss, but not mark the cache entry as invalid. Every time we call a method, under the hood, we're calling send and passing in the method as an argument. And send has become more complicated in YARV. Now it's going to check if it has an entry in the cache for that object type. Then it's going to check if that entry is valid by checking the state of the program against the global state. If it finds the valid entry, it skips to the address stored in the cache. If there's not an entry or the entry isn't valid, it will resolve the method lookup. And if it had to do a method lookup, it will set the cache entry for that class and method. And only after that can it then execute in the method.
So to walk through that, here we have a program at an initial state. Nothing has been run yet, so the cache is empty. We're going to add little yellow boxes to represent when a valid cache entry, when it has a valid cache entry, and we're going to replace that with like an outlined box when the cache entry is invalidated. And to make this a more interesting example, we'll fill out the cast of characters a little bit, and we'll invoke some more methods. So immediately in our program, we're going to resolve these methods. And as we let the program continue to run, we'll fill out some more. And eventually, we have a pretty well-primed cache. For all methods, every additional time it's called, we hit the cache and avoid method resolution. The reason it works in these examples is because our code paths are monomorphic. It's sending messages to the same objects each time. Then something interesting happens. We hit a define method in our Raptor class. This is one of the events that is going to increment generations. And because this changes in the Raptor class, our cache method resolutions for the Raptor class would have to be invalidated. Unfortunately, this is going to also invalidate the entire cache. So all of our methods go away. All of our method resolutions go away. This is kind of a good thing, because if we were to hit raptor.rar again, we need to be able to pick up our new definition of rar. But it's really too bad that we had to invalidate every other class's cache method lookups as well.
Which is a pretty smooth segue to our next section. So to recap, We now know how MRI resolves methods. We know that Ruby 1.9 compiles the bytecode that can be interpreted by the virtual machine. We know how the virtual machine caches the address of method lookups in the bytecode, and because that cache needs to be invalidated, when new methods are available to an object, we know how the global state is incremented when we introduce new methods. Phew.
Good job, you guys.
Let's look at some pictures of dinosaurs and then talk about the limits of method cache as it stands in 1.9.
This is your break. So this one's kind of low def, but it's probably still dangerous.
This one's trying to get some fiber.
And we duct typed our raptors, so sometimes we end up with a stegosaurus that knows how to roar. Okay.
Dinosaurs are awesome, but let's now take a look at what method caching doesn't solve. The first limitation of the inline method cache is that depending on how the application code is written, developers can make the cache useless by clobbering cache entries. The first time it's called passing in Tyrannosaurus, the method lookup is cached with the object type of Tyrannosaurus. The next time it's passed a different object, a raptor, to call rar. The issue here is that even though the address of rar is cached on the first request, since the second call is on a different object type, the cache entry is invalid for that line and overwritten. This points to some conflicting demands. On one hand, we can get well-factored and readable code, but it will also prevent a usable method cache from being set for this line if we keep switching between types. So that's not to say don't use polymorphism, but it's just to point out the cost it could have to the method cache.
A second problem with the inline method cache is that when the cache is invalidated, every single method that has been cached since the program started has to be resolved again. So what we didn't tell you until right now is that there are actually two method caches. There's an inline method cache and a global method cache. The global method cache has a limit of what it can store, and we don't really have control over what's stored there. So that global method cache is also expired by updating the global state. So we have entries in the global method cache marked with the global state of the program when they were cached. And we have inline method caches also noting the global state when they were cached. Updating the global state expires all of these caches and is going to require all new lookups. So this is a good opportunity to look at what updates the global state. Oh, in this example, we have tons of things cached. However, even updating constants, if you update it in the wrong way, is going to cause a new generation. So here we're setting raptor toe count, and that will cause a new generation, and all of our cache is busted. And this point was made, I think, first and most eloquently by James Golick in a great blog post about 6 months ago, where he profiled his company's website and found that they were spending a ton of time building up their cache and invalidating it again and paying that cost all over continuously. So this is a quote from his post that captures the heart of that problem. We linked to this blog post in our Bitly bundle. His problems may or may not be average. It's hard to really know about this stuff because not a lot of people are profiling it. But it's an awesome read, and you could take some of his tips to start profiling things. So the other thing to note here is that as a trade-off for the low overhead cache, we are stomping on the whole cache all at once.
And the last limitation that we want to point out with Ruby 1.9 method cache is expiring the cache isn't always a shortcoming. There are many ways in Ruby to make a method available to an object. And in order to check that more methods haven't been defined for a given object, we need to expire the cache when an event happens that could possibly change the methods defined for that object. Now we're going to touch on some of the things that will expire the cache. The point in these examples is that they are the things that change the set of methods defined and sendable to an object. And if we're going to call a method after one of these things happen, we shouldn't keep our cache because a new method could have been defined that should have taken precedence over our old method. Charlie Somerville's blog post that documents the 18 things that will update the global state and therefore expire the cache, both the inline cache and the global cache, is linked in our Bitly bundle. They fall into a few broad categories. The global state is updated whenever you define, alias, or remove methods. This is the most obvious reason to invalidate the method cache, because adding and removing methods can directly impact where a particular method should resolve to. Consider the above example. On the first call to rar, The method is cached to point to dinosaur. However, after dynamically defining a method on the clever module, an identical call to rar will now resolve to a different location. To account for this, calls like this will update the global state and validate the cache.
If you read through Rails code carefully, you can run into a trick they sometimes use to define methods on the fly without updating the global state. But just like a Jedi must craft her own lightsaber, this one's probably best left as an exercise to each person.
For similar reasons to define method, using alias method will also increment global state. After aliasing growl, the cache is invalidated so that rar can correctly resolve to raptor. And as you might imagine, remove method will also increment global state and invalidate the cache. After removing rar, the cache is invalidated so that rar can resolve back to dinosaur. And there are a few other less common things that can also invalidate the cache by incrementing the global state. Like we saw in an earlier example, modifying constants will bust the cache because constants share the same global state in Ruby 1.9. Also, because of this, auto-loading constants, which specifies where the constant is located, will also bust the cache. And since the OpenStruct class defines accessor methods dynamically when created, and some non-blocking methods also perform dynamic programming to extend modules repeatedly, also invalidate the cache. OpenStruct can be used if you want to use an object in place of a hash. Sometimes you use it really innocently, like maybe you want to pass an object into a template instead of passing a hash. For instance, if we want to do something like this, we're using a hash of options about teeth and feathers to create a new object that gets passed into our ERB template. Unfortunately, if we check out the definition of new OStruct member, we see that we're defining a getter and setter using define singleton method, which will increment the global counter. We're incrementing the counter twice, actually, but once would be enough to invalidate the cache. And it's somewhat common to use OpenStruct casually when you would rather have an object, so it's probably an unexpected invalidation of the cache. So here we're giving another shout out to Charlie Somerville, who created an implementation of OpenStruct that won't invalidate the cache. It's included in our Bitly bundle.
And one last thing to touch on that can invalidate the cache is refinements, which are a new thing in Ruby 2. So if you've ever monkey patched a library before and then you've had the problem of not being able to pull in subsequent version updates, refinements are the thing for you. Unfortunately, they'll also invalidate your method cache, so know that before you start using refinements too wildly. So that's method caching in Ruby 1.9. It's kind of a lot of drama. So we're excited to introduce some new ideas that we hope are in Ruby's future. Right? So James Gollock's post about how much time his company's website was wasting when they cleared out the method cache pretty regularly comes with code. He has a branch of Ruby, which we link to in our Bitly bundle, if you're not already all there, where he creates a more finely grained cache. So it trades the awesome simplicity of the current inline method cache system. Like the inline method cache has this one great virtue of being really simple. And he's going to trade that for being able to invalidate a cache only for a class and that class's dependents. So let's walk through what that would be like. The generations are going to become class contextual rather than universal generations, meaning an event that bumps the global state will only affect the method cache for that class and that class's dependents. To demonstrate this, let's go back to our program that has run for a bit and kind of warmed up its cache. This time, I've changed the code a little bit. I've added the Tyrannosaurus class in, and it also inherits from dinosaur. And this time, when we hit our define method in the raptor class, we do indeed increment the state and cause a new generation, but it's only a new generation for the raptor class and its dependents. Next time, so we won't increment the generation for the Tyrannosaurus class. The next time those lines are executed, they'll be able to use the method cache without having to go get a new method resolution. So I just added in this defined method on the dinosaur class. So this is going to increment the generation for all of the dependent classes, meaning that it will, when we execute define method on the dinosaur class, we bump the generations for dinosaur, raptor, and tyrannosaurus. If any of those lines are executed again, they'll all have to be re-resolved. So earlier we pointed out 3 things to remember about the method cache in Ruby 1.9. First, you can write your code in a way that multiple objects go through the same code path, and so you'll never get the benefit of caching. Second, updating the global state invalidates the entire cache. And third, we talked about the specific things that will cause that new generation. So if this version of Ruby that James Gollick is running were to make it back into trunk, it would eliminate our second point entirely. And it would probably have a noticeable performance boost for very large applications, Ruby layers. In other words, with these changes, the dinosaurs stomping out the cache just got way smaller.
So we want you to take away a few main points from this. First, don't do tricky things like define method or defining a constant on the fly. Don't define anything on the fly unless you have a good reason or are aware that it will update the global state of the program and invalidate your method caches. Second, the gems and libraries that you use will often try to do this. Some of the gems that make the most use of these tricks are ones that you would use only during development, and that's fine. And as an example of this, defining methods at runtime is what RSpec is built on. Here's an example taken from RSpec. But we don't really need to worry about these tools that we use in development. The app probably won't run long enough to warm up its cache in development anyways, and we get a ton of utility from these tools. So it's really libraries that are included in production environments that you need to be aware of. And lastly, if you really need performance improvements in the Ruby layer, take a look at the work we've referenced from James Gollick and Charlie Somerville. And links to our GIST blog articles and everything we referenced is in this bit.ly bundle. We're going to end this talk now, but if you want to discuss it more, please come talk to us. Charlie's here around here too, so we can hopefully steal him for some questions as well. Thanks for listening to our talk.